Welcome back for another session of BE Civil Structural. Today we are going to talk about seismic. It is an important subject where at least 3 to 5 questions will be presented in the exam. But no worries, I will cover the most important points, and in the description I provided a solving examples book where in this session I will tell you the most important chapters and the most ideas that I found in the exam. At least, as I told you, at least 3 questions was presented in the exam. So let's start. We will start with a brief about seismic. I will tell you over and over again to be prepared for theoretical questions in any part. The seismic are generated because of the movement of the tectonic plates, which can be generated because due to explosions or volcanoes or the natural movement of plates itself. So the source point, it is the focus, and the point at the surface, it is the epicenter. Okay, so the focus, it is the source, and the epicenter is at the surface. Where, as you can see, there is the hanging wall and the foot wall. The foot wall, it is a stationary wall. It will not move. However, the hanging wall, it will move. And these moves, it categorized into 3 movements. The first one, it is called the normal fault. Okay, so the hanging wall will goes down and the foot wall will stay still. And the other one, it will be the reverse fault, where the hanging wall will goes up and the foot wall will stay still. The other one, it can be divided into two. It can move to right or can move to left. So the strike slip fault can be called as left strike slip fault or right strike slip fault. It is important to know the movement between the tectonic plates of the ocean and the continent, where this motion called subduction. Okay, so when the tectonic plates from the ocean at the ocean it goes to the continent, they usually go down below it in a movement or in a definition called subduction. Okay. So let's understand the seismic waves. As I told you, the source of the seismic, it is the focus. Okay, and it will generate waves. There are 2 types of waves: the body waves, which can be consisted of primary waves and the secondary waves, and the other type, which is called the surface waves. And they are divided into the lava waves and Rayleigh waves. It is also important to understand the waves that is generated from the seismic. So the first one, which is called the body waves, it is the fastest one, where it is moves in a straight line, so it in the shortest path, so it can go its movement is straightforward, whether in expansion or contraction, as you can see. So the B waves, which is called stands for primary waves, can be compression or can be expansion. Also, these waves they travel through solids, liquids, gases. Okay, so they don't, even if there is liquids the tsunami and so on. I think that is generated due to the B waves, maybe because the secondary waves they are just travel through solids. Okay. However, the primary waves, they are higher speed and travel through solids, liquids, gases. Their movement is in a straight line, compression or expansion. However, the S waves, they like normal to the movement of the waves. Okay, and they are more destructive. And they are lower in speed. However, the surface waves, so after there are forces generated due to the body. Okay, so it moves from the focus to the surface. There is also the surface waves, where it will generate 2 types of waves. The first one, which is called the lava waves, and the second one is called the Rayleigh waves. The lava waves also, it is the same as B. It is faster. It is in horizontal motion, as you can see. The Rayleigh waves, it is in horizontal motion. However, the Rayleigh waves, it has an elliptical motion. So the Rayleigh has an elliptical. However, love waves, it has like a horizontal motion, and it is more destructive. So in this part I want you to to take the definition and to understand them, because it is important to know that the focus, it is the center, and the epicenter at the surface, and that is called the seismic waves, the hanging wall, the foot wall. Just to understand the definition, the reverse, the normal, what does it mean by the normal, what does it mean by the reverse? Reverse is the compression, normal is the extension. Just go through these slides and understand them, just even for general information, because there are some theoretical questions can be presented in the exam. Now let's talk about the diaphragm. The diaphragm is the chapter 1 and chapter 3. Okay, so in the description I will provide you with this book. Okay, it is like the most important book, called by Majid Baradar. It is a very important book, where at least 3 to 4 questions was presented in the exam having the same idea from this one. So I highly recommend you to dig deep into this one, and to spend a lot of time. Especially this one, it has questions, and at the end for each chapter it will has solutions with explanation to each one of them. So it's like since the hanging wall is a thrust upward and over to support wall, it is a reverse thrust fault. So it is very important, chapter 1 and chapter 3. And don't worry, when I will go to the diaphragm part in the next slides, I will go through the main ideas, and I will talk to you what are the main ideas that you need to focus on. Also, I highlighted to you what are the most important pages. Also, the same I will do the same I done in each in the ASCE and in the IBC and so on. I highlighted to you the most important questions that you need to focus on, and also in chapter 3 it is very important. Also, this one, chapter 3, is the diaphragm theory. It is very important, at least 3 questions regarding the flexible diaphragm and rigid diaphragm and so on. The one that highlighted in green, it is not related to us. However, in the yellow you must focus on them. If I were you, I will solve chapter 1 and chapter 3, because at least 3 to 5 questions will have the same idea. So I highlighted you in the book, and also highlighted you to the most important pages. And in the next slides, when I will reach to the diaphragm, I think in chapter 12, we will talk about it more closely. So now let's start with chapter 11. Now seismic details and requirements are still needed even when any lateral force like wind forces exceed the earthquake. Like for an example, if you have like a steel shelter, okay, I have a steel shelter, and this steel shelter, of course, it has cladding, so it is a steel shelter. Okay, and of course, like in session 3, we calculated the size, the wind force, and I told you that the minimum wind force is 0.77 kilonewton per meter square. Okay, for the walls. So I will calculate that on this this surface area, and of course the wind, it is directly proportional with the surface area. Okay. However, I'm in the seismic design category for this building is C, so I have a seismic design category C, and I am using ordinary moment frame, so I am using R equal to 3.5. So still, of course, the steel shelter, it has mass, it has a lesser mass than regular buildings. So the effective weight acting or generating from this building is very small. So the expected base shear, which is equal to CS multiplied by the effective weight, okay, it will be of course less than the wind speed or the forces generated from the winds. Still, I need to apply the details because I built a hypothesis that the building will exhibit a response against the seismic. So if I didn't do the details, this building will not exhibit the same requirements that I'm trying to establish. So even so, the dominant force is the wind. Still the seismic detailing is very important. So maybe this question like be theoretical, may because it defines if you understand the code itself or not, and understanding the requirements from this code and from the seismic details or not. So even the seismic details and the seismic force is not governing, still the seismic details is very important to apply. Also, I want to talk about the types of buildings. There are two types of buildings. The types of building, let me. So we have buildings, of course, that people live in them. So that is a regular. So we have inhabited by people. However, we have non-building structures. These non-building structures can be divided into similar to building, okay, and not similar to building. So I'm talking about that because in this part it specifies that buildings whose purposes is to enclose equipment or machinery and whose occupants are engaged in maintenance or monitoring of that equipment, machinery, or their associated processes shall be permitted to be classified as non-building structures. Okay, so if they are classified as non-building structures or not in this part, non-building structures, so I will use chapter 15 in the design. So if in the exam he tells you that I have a building and it had equipments, so it inhibits equipments, not people, so of course I will go to chapter 15. However, if he tells me that this building habits people, okay, not not equipments, then I will go to chapter 12. So what I'm trying to tell you that you must understand what type of building you are going to design, because each one of them has its own purpose. Also, another important definition, we will always in the code it will talks about the components, attachment, and support. This one from the commentary, the components meaning that any equipment. So the component it is any equipment, and the attachment it is any like the fixation bolt. As you can see, it's like I think it is undercut anchor bolt. And the support it is like the clip angle or the base plate. So it is important to define the components, attachments, and support and so on, because chapter 13 it is dedicated for the component, calculating seismic force on it. Now, another important definition is the base. The base, of course, it is very important because it will affect on the effective weight and the height of the building that we are going to calculate. However, the definition of the base, it is the level at which the horizontal seismic ground motions are imparted to the structures. What does it mean? So, if you have like ground floor, that is the ground. So I have a building. Of course, that is the foundation. So we are actually dealing that the seismic force that will act, the level at which the base shear will act on the building, it will not be here. Okay, we consider it at the top of the foundation. So the base shear will act at top of foundation in this case. Okay, so that is the base, and of course we from this point to the top of the building, that is the height. So when I'm trying to calculate the time approximate, as we are going to see in chapter 12, which is equal to ct power multiplied by h power x, I think. Okay, that is the height. So that is the height of the building. And when we are going to calculate the base shear, which is cs multiplied by the w, which is the effective weight, it will be the weight starting from this position to the up. Because in some cases we will have like a basement. So if I have also that is the ground, and I have a building. However, in this part I have a basement. So that is the basement. and this is raft. So this is a raft, and this one is basement. So at which, and that is like the ground floor. I have a ground beam here, and that is the first story and second story and the roof and so on. According to ASCE, the location at which the base shear will affect usually if you have like a basement and it has no openings, okay, because there are a lot of parameters depending on which location the base shear will act. Depending on the if you have a basement or not, if it has opening or not, the lateral system, resisting system, it is completely from the top to the bottom, the type of the soils around you, okay, if it is loose or it is stiff soil, and so on. However, in this case, it will act at this level. So the base shear will act at this level. So the height you are going to consider, that is the one, and the effective weight from this place. So let's go back to the slides again. I am in this table. I'm telling you that the columns supported on footings or pile caps, the base location is the top of these elements. So you must understand them, because in the like in the exam he will give you like a building here, and he will tell you you have a basement with no opening and so on. So what is the base that you are going to consider, and what is the H, and of course and so on. He will tell you that you have an effective weight here, or a dead weight here, and so on. I will not consider, in this case, I will not consider the dead weight from the basement, okay. Also, if you have a vertical elements of seismic force resisting systems are supported on top of perimeter foundation walls. So if you have a foundation walls, not columns and so on, so you have a foundation walls and the structure is supporting on them, then it is the top of the foundation walls, because the foundation walls, of course, they have a rigid stiff, meaning so if you have a building, and this building that is the ground, and this part it is a structural wall. So you can imagine that if I draw a section, if I cut a section, if I draw the plan, it will be like this. So it is very rigid system. So the base shear will act at the top of the elements supported on the foundation walls. Also, the vertical elements are supported at various elevations on the top of footings, pile caps, and the perimeter foundation. The base is the lowest elevation. So if you have a structure, okay, if he give you like a structure, the same structure, and you have like this on two different elevations, I know that is weird. However, that is the case that he is talking about. Then it will be based on the lowest one, okay. So again I recommend to focus on the definition of the base, because if he give you an example or give you an equation regarding the base, you must understand at which is the level the force will act on it. The second one, of course, the structural height, as I told you, it is a vertical distance from the base. Okay, so it is starting from the base to the highest level. As I told you, it will be the base, like from here, that is the base, to the highest point. Seismic force. As I told you, there is something called here component. Okay, according to the ASCE, the component can be considered as a flexible. The non-structural component that has a fundamental period greater than 0.06 second, then it will be considered as a fundamental that is flexible. Component structure as a part of an architecture, and also component non-structure, a part of an architectural, mechanical, or electrical system within or without a building or non-building structure. That is the definition of the component. Okay. Also, there is something called the flexure control diaphragm, and this part we will talk about, but you must understand definition of flexure control diaphragm. Okay, let me talk this one brief. So if you have a building, okay, that is a plan, and I have a shear wall, and I have another shear wall, and I will consider this one as a rigid diaphragm, okay, because it can be rigid or it can be flexible. And I have a lateral force coming from seismic. So in the I can consider this diaphragm. Okay, if I wanted to simplify this system, I can consider it as hinged, the shear wall as a hinge, and another shear wall as a hinge, and I will consider this diaphragm as a deep beam maybe. So I can consider it as a deep beam, and of course this force coming down from here there, so it will have like a moment like here. So this one will have tension, okay, and this part, by the way, it called the chord, and this one will be of course will be compression. That is why it is called flexural controlled by flexure, because it acts like a beam. Okay, that is why flexure controlled diaphragm, because it may be flexure controlled diaphragm. There are two types: flexural controlled diaphragm and a shear controlled diaphragm. Another important definition: the inverted pendulum type structures. It is a structure at which in most 50% of the structure mass is concentrated at the top of a cylinder cantilever structure, and so on. Of course, that is the one that is the same for a water tank. If you have like a water tank cylinder shape and just supported on types of on columns, so that is the one. So the most of the mass is concentrated at this location, and this shape actually behave as a single degree of freedom. It is almost a type of building that act as a single degree of freedom. Okay, when we will talk about effective length method, effective lateral force, ELF. Okay, equivalent no the equivalent lateral force, and the response spectrum. The response spectrum, it is based on a single degree of freedom. Okay, we will talk about these two methods, the equivalent lateral force and the response spectrum, later. However, this type of building, the inverted pendulum, it acts like the single degree of freedom. Okay, and it has own requirements to satisfy. Another important point, as I told you before, the non-building structure similar to building. You must understand the differences, because the similar to building, it can, as it will tells you here, it can use chapter 15 and chapter 12 in the design. So here it says a non-building structure that is designed and constructed in a manner similar to buildings. So if I have like a process structures, I have a structures, okay, and this one it has equipment like a vessel, okay, like HVAC and so on, maybe whatsoever. No people inhabited on this building, so it will behave similar to building. It responds to strong ground motion in a fashion like buildings. Also, it has a basic lateral and vertical seismic force resisting system. What does it mean? So I have, like here, I have a moment frame, and this direction I have like concentric pressed frame, so it uses the same statical system, so it can behave like a building structure. Of course, the most important SS and S1, the acceleration, spectral acceleration for the short period, the SS for short and the S1 for the period of 1 second. And of course, we must know the site class. In chapter 20, we will go through the chapter 20 how to identify the site class. Of course, another important definition is the seismic design category, because based on this seismic design category, the requirements has been given in the chapter 12 and so on regarding the seismic must be fulfilled. So let's now talk about seismic design criteria. It is highly recommended when you at the start of a project and so on, you must know the SS and S1, because the SS and the S1 they are very important, and the risk category of the building, as we saw in session 2 regarding the loads and load combination. So I have a risk category, and the SS and the S1, they are most important because they will specify which seismic design category my building will be placed. And according to seismic design category, will be some requirements that you need to fulfill. So a rule of thumb: if you have an S1 lesser than 0.04 G and SS lesser than 0.15 G, the structure is permitted to be seismic design category A. And in this case, the minimum lateral forces you need to specify, as I told you before. Let's go back here. The 1% of the weight, that is the minimum force that you are going to achieve. Okay, that is the minimum you are going to achieve. So even you are seismic design category, you need to achieve the minimum. So the steps to determine the seismic force. Of course, the first thing you need to determine the site class. The site class, according to chapter 20, if you have enough information, and we will see it later when we will go to chapter 20. If no data available, assume site class D, and that is based on the ASCE. So as I told you here, component flexible, component rigid, and as I told you before, I'm highlighting you the most important part. There is a collector, drag strut tie, so you must focus on them. Inverted pendulum, seismic design category, and so on. So here, where the soil properties are not known in sufficient detail to determine the site class D subject to requirement shall be used. So it is very important, because in the exam he may not give you the site class. If he doesn't give you the site class and it doesn't give you enough information, like in chapter 20, I don't want to go right fast about it, then you can assume site class D. So I have my site class, and then you can determine the FA and FV based on SS. If he didn't give the SS and the S1, there will be maps, and we will tell you later that there are maps, and it is the same as the wind. You need to know the states, but I don't think he will do the same, because it is difficult, okay, because it depending on the latitude and longitude of the location of the building. And I didn't see that he will not give you the didn't any question that you need to identify the SS and the S1. He will give you the SS and the S1. However, the site class, if he didn't give you, it can be assumed as D. So you can determine the FA and FV. Okay, this is the one. So after giving the SS and S1, I need to determine the FA and the FV. It is the FV, it is a short period site coefficient, so I need to know the site class. So to need to know the site class, if I don't have enough information, I will use D, and from these tables, the FA, I will, okay, that's also important, I will get according to which ones I will get the FA, and from here I will get the FB. Okay, so after getting them, I will get the SMS. The SMS, it is related for the seismic maximum considered earthquake, and the SDS, it is the design spectral earthquake, and for the short period, and here for the 1 second. So after that is the one that I'm going to design my building on them. So after knowing the site class or assuming it, and knowing the SS and the S1, I can calculate the FA and VV. Then after that, I can calculate the SMS and the SM1 and the SDS and the SD1, because SDS is 2/3 as you saw here, so no problem. Then after that, I will calculate my base shear. That is the idea of how to determine the seismic force. So I have an equivalent lateral force. Yes, you have like response spectrum method. Yes, you have a non-linear, you have time history, and so on. But that is the main idea. I must know my site class, must know my SS and S1. Getting them, I can calculate it. That is the main idea. So as I told you, you must know the site coefficients. Okay, the risk axle. There are two types of the risk targeted maximum considered earthquake, MCER. And there is another one called the MCEG. That is one. Okay, that is the mapped acceleration. I think it was here. Let me see. Yes, that is the one. There are two types, the MCEG and the MCER. We are using the MCER. Okay, there are two types. These ones regarding the probability and the weight of each one. because if you have like, I will tell you a brief about it. That is the place of your, that is the location of your project. So that is my location, and I have like from history data, I have data. So history, this place called 1, and this place called 2, and this one called 3, and of course the distance from each one, and the probability that each one occurs. So this one occurs like 500 years, this one 200 years, this one like 1500 years, and so on. So the MCR, it will depend on the probability and the weight of each one that occurs. So the force of this one is like very high, this one is intermediate, this one is like high, not very high. So MCR, it will give you like an average depending on the weight and so on. However, the MCEG, this one, it doesn't take into consideration the probability and so on. It will take the maximum. However, the MCEG, it is dedicated for calculating the liquefaction, the soil stability, and so on. This is the one, BGA. So if you did need to determine, and that is I think that is this part, it is like for more for geotechnical engineers, and they of course they understand the difference between them. So the response spectrum, it is already existed here, and it has like a brief about it. So let's know about the main parameters of it. So let me draw. So the response spectrum, we all know that is the one. However, this one differs, okay, due to site class. So if I have this, if this one is for rock, okay, then this one will be like for stiff soil, and maybe this one will be like loose soil. So if you have like, so as the site class is high, the seismic force will be high, okay. However, of course, the site class, as it is high, the FA and FV also it has an impact, as you can see in this in calculating the FE. If you have a site class A, then I will multiply by 0.8, 0.8, 0.8. Still, yes, this is one will be high, but still I will multiply by a factor still 0.8. If it is C, then I will multiply by 1.3. But you need to understand the formation of the size of the response spectrum. So you, if any questions regarding it, asking you about like if you have a rock, so it will be like this one, or it will be like this one, and so on. No, so you must understand each one of them. The second thing I want to talk you about is this one. It is the ground acceleration. Okay, so meaning that the building acceleration usually more than the ground acceleration. So at 0, okay, so if I have like a block of concrete, that is a block, and the ground motion will move, so the block will take the same acceleration of the ground, okay. However, if the same ground and I have like a building, okay, so the building will behave differently, and it will have like a higher that is a building acceleration, so it will have a higher, usually it will have a higher from ground acceleration. So that is also an important point to understand what is the building acceleration and the ground acceleration. So at this, it will be the ground acceleration. This point, it will be called the T node, and this point is called the TS, correct? Or let me check. That is the T node, and that is the TS, and that is the 1. And corresponding to the 1 second, it is the SD1, and at the plateau, at the highest point, it is called the SDS. So this here, that is the SDS that we are trying to design on it, and at 1 second we will have like SD1, okay. Also the T node and the TS. TS, I think it is like 5 times the T node. Okay, because it is important to know how to calculate them, because he will ask you how to calculate them. T node, it is 0.2 SD1 divided by SDS. However, the TS, it is SD1 divided by SDS. So a TS is 5 times the T node. Again, you must understand them because it is an open book. He may ask you about anything. So as I told you, the T node, it is important. The TS, it is important. This point, it is the ground acceleration. That is the SDS and that is the SD1. And after the 1 second, that is the long period, the TL, which is usually like 8 seconds. Okay, we used 8 seconds. Some people will use 5 seconds, but however, it depends on the region that you are designing in it. However, we use usually the 8 seconds. Also, to calculate the vertical ground motion, this one we have talked about the response spectrum, but as you can see here, he's just mentioning a response spectrum because we have a horizontal response spectrum and we also have like a vertical response spectrum. That is the vertical ground motion for seismic design, and also he gave you the equation that you can build up your the graph. However, we actually use the value from chapter 12, which is equal to 0.2 multiplied by SDS multiplied by the dead weight. Okay. Regarding the vertical ground motion, we can take it as 0, either in the following condition, and this one it is shown in chapter 12, but I put it here. If the seismic design category is B, okay, and he give you like another equation where determining demands on the soil structure is the SSI of foundation, if there is like interfaces between the soil and the structures, and I think this one will depending on the geotechnical report. So you need to ask the geotechnical report if I need to consider it or not. However, if you are designing a tank, so I have like a tank, so it is filled with fluid, with a liquid. So the most, of course, I will take the EV, I will consider it in the uplift case, especially in the uplift case. I will consider this case in the uplift case if I am designing like a heavy dead weight like a tank. Another important one that I told you before, how to determine the seismic design category. The seismic design category, as you can see here, it depending on the size, the SDS, okay, which is generated from the site class, okay, and the risk category. And there are two tables, one dedicated for the short period and the other dedicated for the 1 second period. And of course, as long as the risk category increases, it will give you a higher seismic design category. Meaning a higher seismic design category, we have into our consideration A, B, C, D, E, and F. F it is the worst, so it is from like good to bad. As long as each one has its own requirements that you need to fulfill. And there are two types of there are two tables that you need to achieve for the short period and for the 1S period. However, in this one, it gives you like a condition where you can use the short period. However, these conditions, when you will read it, it wants to make sure that the structure is in this area. Okay, it is located in this area. He wants to make sure that it is located in this area, so you can use the SDS. And I don't think this criteria in our work I can fulfill it, because it has like in each of the two orthogonal directions the approximate fundamental period of the structure TA determined is less than 0.TS, which is 0.TS, which is that is the one. It has like very hard rules to fulfill. However, if you want to identify the risk category, as I told you, the SDS, and this is the one for the SD1, and according to the risk category, you can specify which risk category. So so if you have an example, in the in exam, he doesn't tell you the site class. So if he doesn't tell you the site class, assume D. That is the idea of the question. If you don't know that, I can't calculate the FA and the FB, even he give me the SS and the S1. So I need to assume site class D so I can calculate the SMS and the SM1. Okay, and he will tell you like you have a residential building. So this residential building, I can, from the risk category, it will be like 2. So after that I can calculate which seismic design category my structure. So in the choices it will tell you A, B, C, D. I choose which one of them. Okay, so that is the idea. It is a simple idea of an exam. Yes, he can give you like that is the type of the questions that you will see in the exam. If you don't know where you are going to find the answer, you will not be able to solve it. However, if you know that if it doesn't give me the site class and I can assume it as D, then the equation or the example will be solved in like 2 minutes. So let's go back here. Also, I give you in this part, however, I don't consider it. He give you like if the structure shall be assigned to a seismic design category in according with this section. He give you like some notes that you cannot the tables if you have this condition, like in risk category 1, 2, 3. If the S1 is more than 0.75, then you will have used to seismic design category E, and if IV S1 is more than 0.75, then it will be F. Okay, so let's go back here. The SD1 is more than what? So if you consider 0.2, but however in here it tells you 0.75, 0.75, so it is very like a very large value. Now chapter 12 is dedicated for the building structures general requirement of them, that they must have strength, stiffness, and energy dissipation capacity. What does mean by energy dissipation capacity? So if you have a moment frame or a frame, okay, so we all know that we design it based on strong column, weak beam, strong column, weak beam, and according to the weak beam we can create a plastic hinge here. Okay, if you have like a shear wall, so you can create a plastic hinge here. If you have like an eccentric breast, so we have like this called a link, and it can dissipate the forces. So that is called the energy dissipation. To withstand the design ground motion within the prescribed limits of deformation and stress demand. Also, the design ground motion shall be assumed to occur along any horizontal direction. However, as I told you, the seismic design category affects it has an impact on the horizontal direction. If I am designing for seismic design category C with type 5 horizontal irregularity, the type 5 horizontal irregularity, so I have like an inclined shear wall. It will tell me inclined shear wall, and I have seismic design category C. I will need to assume 100% from a direction and 30% from other direction. Okay, if I am designing for seismic design category T and so on, I will use this also 100% plus 30% from the other direction. So it tells you here that the ground motion can be assumed in any direction. Also, this part was mentioned in chapter 1, the continuous load bus and so on. And as we know that any smaller portion of the structure shall be tied to the remainder of the structure with elements that have a design strength capable of transmitting. Here it tells you that it is the greater of. Okay, so if we go back to chapter 1, we can see that that is called that the connection shall have a strength to resist a 5%, not this one. I think the 5%, this is the one. Or any smaller portion of the structure shall be tied to the remainder of the structure. It has the same text even so. However, in this part, it will tell you in a smaller portion that have designed for symmetric torus of 0.33 0.133 multiplied by SDS multiplied by the weight. Okay, that is the one, the weight of the smaller portion, or the 5% of the portion's weight, so to achieve the continuous load bus from chapter 1. So it is important because, as I told before, if he brought you like a building and you have like a smaller building and a small attachment, so the connections, this one will need to transfer at least 5% of the portion's weight. However, regarding for the seismic, at least 0.133 multiplied by the SDS multiplied by the weight of the mini portion. Okay, so if I have like a 3 connections of a steel beams, so each one of them will so it will be divided on the 3 of them. Another important point, also the connection to the supports. It is the same one in chapter 1. A positive connection for a resisting horizontal force acting parallel to the member shall be provided for each beam, girder, or truss, a minimum design strength of 5%. So I'm going to design, I'm designing for a connection to the supports, at least consider a minimum of horizontal force. Okay. Now we will talk about the table that is a structure system selection, and let me open it from here. So it tells you this table. It will tell you that this one is used for the buildings. Okay. It tells you what is the seismic force resisting system, depending on the statical system that you are using, and that is called the R, the ductility factor or the response modification factor. Okay, that is the one which we can divide the actual force, because let me draw something. So I have, of course, we know the relationship between the force, okay, and the delta. So I have the force is equal to the stiffness multiplied by the delta, and if I consider my structure behaves linearly, then it will be something like that. That is called the Fe, that is the elastic, the force of elastic, and of course there will be the delta elastic, that is a delta or U. Maybe let's call it delta elastic. However, we divided this elastic, the Fe, by R. So after dividing it by R, it will be like the F design. So it will be that one, this one. So my structure will behave like this. However, it will exhibit more deformation and more response. So it will go like this. And of course, that is the yield point. And it will be, here is a delta ultimate. And the area under this area, under this curve, it will be the ductility. Because we all know that my system will exhibit like a permanent deformation and so on. That is the one that is used like for moment frame. Okay, and we have another that is called the hysteresis it exhibits the amount of deformation that your structures has been imparted upon by the seismic force. So what I'm trying to say here, depending on the eurostatical system, there are the R factor and the overstrength factor and the CD, the amplification factor. That is the one. So if I want to get the delta ultimate, so I have the delta here, I will multiply by the CD to get the delta ultimate. Okay, we will talk about that later. But here, of course, A, it doesn't mention here, because if it is if the SS is lesser than 0.04 and the S1 is lesser than 0.15 G, I just need to satisfy the 1% of the dead weight as a lateral force. For each one of them, the seismic design category and according to the lateral resisting system. So let's talk about like a steel eccentrically braced frame. NL, it means not limited, however it is 160, it is in feet. Okay, so it is in feet. And 100. Ordinarily concentrically braced, as I told you, it has a limitation for D. In C, not limited. Okay. and so on. So if I want to find the R or omega or the CD or the limitations, even so, maybe he will give you like a questions. It will be an easy one. He will tell you which statistical system can be used in seismic design category D. Okay, so I have which statistical system can be used, and he will give you like 4 choices. Can be used for seismic design category D, and its height is not limited. Okay, so you will have to go through each one of them and to see which one satisfies this criteria. So it is an easy one. However, the most and it is very like a tricky question. If he tells you which statistical system, not specifically detailed for seismic resistance, what is the least R can be used, considering without considering the lateral, without considering the detailed for seismic resistance. This part in H, he tells you that the steel systems not specifically detailed for seismic resistance, excluding cantilever columns, I will not use the detail. So if I use R equals to 3, I will not consider any requirements or any detailing requirements. So I will not go to ISAC 341. Okay, I will not go to this area because I am designing for a larger force. Because if I have like a ordinary moment frame, so I have a steel ordinary moment frame, the R which is equal to 3.5. So if I use R equal to 3, in this case I am designing for higher forces. Okay, so due to designing on a higher forces, I will not using the detail. Of course, if you don't want to consider any seismic details and so on, you can consider R equal to 1. If you consider the R equal to 1, then you don't have to go through all of this. You took the all force and you will design on it. But it is, of course, it is not economical, and you need to get the benefits from the ductility of the materials. So that is the table that you need to also to understand, and of course that is the cantilevered column. This one for the C for the moment frame. This is the one for the dual system if you have a special moment frame. And it tells you that at least 25% must be resisted by it. There are also the building frame system, concentrically pressed. So you must get yourself familiar with the location of them, so you can able to solve the problem quickly in the exam. Here it is NL not limited, NB not permitted. So in some cases it will not be permitted. Also, we will talk about the combination of the framing system in different directions. In our design, we usually consider like shear wall in a direction and like a moment frame in a direction, or we may consider the same systems in the same directions, or we can use two different systems. I can use a moment frame in this, and I can also consider a shear wall in the same direction. So in this part it talks about the combination in the same direction. I will combine the framing system in the same direction. So what is the value of the R that I am going to use, and what is the CD, what is the over strength. So if in this example, if I have like that is the elevation, so if I have like 3 columns here or 4 columns, and I consider this, that is the symbol of the moment. So I have like a special moment, and at the same time I have like inverted V brace. So I have a special, and maybe I will tell that is a concentric brace, ordinary, not special. So this one it has an R equal to 3.25, and this system it has an R equal to 8. So if I consider this one alone by itself, it will has a lower force, because as I told you, this one, that is the force and the delta, I divide the F elastic divided by the R. So as I divided by a large R, so I will have a very small design. However, here it is 3.25. So maybe the force it will be like here. So the force generated or exhibited by this system will be higher than the special moment frame. So in this case, of course, he will tell you that You will use the least value. As I told you, the least value, what does it mean? The R is equal to 3.5, not R equal to 8. You will use the corresponding of the CD. Okay, it will give you like also a theoretical example. You have two systems, one is a concentric brace and one is a special moment frame. Which R you are going to use and which CD are you going to use, and overstress you are going to use, and he will give you 4 choices for each, and each choice has 3 values for the R, CD and omega. So you must consider that you are going to use the least R and the corresponding of the system. So I will use the CD, which is equal to 2, overstress which is equal to 2 in this area. So I'm going to use the steel ordinary concentric brace frame. So the omega is equal to 2 and the CD is equal to 3.4. Okay, and I will use the 3.4 if I am combining in the same direction. Also, if you have a vertical combination, so in this case also I will draw 2 cases. That is the case 1 and I will have case 2. So here it is telling you that if you have like very rigid, that is X brace, and this one it is the opposite, and that is the one it is frame. I have the opposite. I have a very rigid, and this one is moment frame. So that is called moment frame. That is a brace system, and that is a brace system, and this one is moment frame. So this one is rigid and this one is flexible. So in this case you are going to design the R top. I am going to use the R top and the corresponding of the R. However, when I am transmitting this force into this part, I must consider multiplying by the R top divided by the R bottom, because the R top is higher. So to consider a higher force on this one. Okay. However, this case I will use the R top. The R top is less than the bottom. Of course, it will generate a higher force, and so there is no need to magnify it. So in this case, the forces here shall be magnified when it is transmitted to the lower portion. That is what is being described in this table. Case 1, lower system is stiffer, so I have like an X brace than the upper system. The design coefficient R, omega, and CD for the upper system are permitted to be used to calculate the forces and derivatives of the upper system. For the design of the lower system, the design coefficient for the lower system shall be used. Okay, so there is no problem. The lower system is flexible compared to the upper system, so the design coefficient for the upper system, which is has the lowest R, so it has a higher force, shall be used for the both systems. It tells you that you have an exceptions to consider this case if you have like a rooftop structures not exceeding 2 stories in height and 10% of the total structure weight. So if I have a building and I almost 2 height, so it is 2 or equal to story, and its weight is lesser than 10% of the weight of the building. Okay, so I don't consider this as a special case to consider the lower and the bottom. Also other support structure with a weight equal to or less than 10%, so I will not consider this case. The one that I was talking about to magnify or not to magnify that is called the two-stage analysis procedure. Okay, this one it tells you that if the I lower is is stiffer than 10 times the I upper, and the T structure is lesser than 1.1 T upper, he tells you that you can use a two-stage analysis using the equivalent lateral force. Okay, so I will draw this building again. So I have a very stiff lower part, and here very flexible. So if the inertia of the lower more than or equal 10 times the inertia of the upper, and the T total structure is less than 1.1 T upper, okay, I can consider two-stage analysis. Considering two-stage analysis, it is important, especially in the equivalent lateral force procedure, because this case it will not behave as a single degree of freedom, because it will have a different behavior. Okay, also due to the time period of the structures, as we will see later, that the vertical distribution, it has a factor like wi multiplied by the h multiplied by h with a factor k, and this factor k, as the time period like more than maybe 1 second, it will have a like 1.2 value or 1.5, and as long as the time period of the structure increases, the top part of the structure will carry additional forces. So to make it short, it gives you like a two-stage analysis. You can use equivalent lateral force for the first one, and then transmit the forces from the upper part to the lower part. However, you need to magnify it by the upper part, this value, divided by the lower part. Okay, what is this rho? Rho, it is a redundancy. We will talk about it. However, if the upper part has more redundancy than the lower, then this will be 1, and this one will be 1.3. Okay, so it tells you that we will take also the consideration of the redundancy. We will talk about the cantilever column system. The cantilever column system, it actually exhibits the same way of a single degree of freedom. So he gives you conditions that you need to specify, that the B actual is less than 15% of the B available, including slenderness effect. So if I am going to use I have a slender column or a cantilever column, okay, and it carries so I have a steel frame or a steel column and carry a pipe, okay, so that is the height like 5 meters and so on. I at least must satisfy the B actual, okay, is less than the B, so it's less than 15% of the B available. So meaning that the interaction ratio due to axial force is less than 15. Okay. Also, the foundation and the other structure must be designed including overstrength. However, don't get scared from the overstrength, because in the case of the cantilever, it is equal to 1/4. So if I have a steel ordinary cantilever column system, I will multiply by the forces by 1/4, so it is not a big deal, so don't get afraid. However, this is the condition that you need to meet for the cantilever column section or column system. As we talked before, the inverted pendulum type structure supporting columns or piers of inverted pendulum type structure shall be designed for the bending moment calculated at the base. In this part, it tells you that if you have the same thing, if I have a tank at the top, so if I drew the bending moment diagram, it will be something like that. So I have M1, and that is one is half M1. That is the idea. It tells you that the distribution of the moment, it will be uniformly to a moment at the top equal to 1/2 bending moment at the base. Reduction of foundation, also it is important. Overturning permitted to be reduced by 25% if the equivalent lateral force is used. The structure is not an inverted pendulum or cantilever column structure, because the equivalent lateral force, it is based on a single degree of freedom, and the inverted pendulum or the cantilever column structure, it acts the same behavior of the single degree of freedom. Okay, meaning that to reduce 25% for not these systems, okay, we understand that these systems, they are representing the actual representation of the equivalent lateral force, because we all know that. Let me draw a response spectrum. So the response spectrum, so they need to draw it. They bring a seismic force or a ground motion, an earthquake, and apply it for different buildings. With this one, it will have a T1, T2, T3, and of course this building, it will be something like that with H1. This one will be H2, and the third one will be an H3, and so on. And they put the maximum response. Okay, so they represent or graph the maximum response from each one of them. Of course, these procedures can be it is used for different ground motions around the location, so they can able to make a unified response spectrum for all the types of the seismic force that is exhibited into the location of concern. So when the structures of mine, it is actually like this one, it is an actually inverted pendulum, so I don't need to reduce 25%. However, in the case of using like a frame or a building, okay, a building, and I can be reduced 25%, meaning that these forces, meaning that the equivalent lateral force, it is very conservative value. Also, there is a 10% reduction if you are using the model analysis requirements, which is the of this section, it is a response spectrum. Another important topic, of course, the horizontal structural irregularities. These types of irregularities, it will affect our assumptions of the design, and it will have an impact on the actual analysis that you are going to use, whether you are going to use the response spectrum or the equivalent lateral force and so on. So for the horizontal, we have 5 types. Okay, for the torsional, we have irregular and extreme torsional irregularity. As you can see, that is the delta minimum and the delta maximum here, and that is the delta average. So if the delta average, the delta maximum is more than 1.2 tilde average, so it is like there is a torsional high in the building. If it is more than 1.4, then it is extreme. However, torsional irregularity, consider the AX. The AX will consider that is accidental torsion. However, for this type of irregularity, it can only be considered for a rigid diaphragm. So if you have a flexible diaphragm, it cannot be considered. Okay, so if I have a flexible, I cannot consider it. Also, there is the irregular shape if it is more than 0.15. Of course, there is a diaphragm discontinuity. It's like I have a floor has an opening, or the stiffness of the floor has been decreased. Okay, so I have like a thickness 20 centimeter, and the section then the thickness of the floor became like 15 centimeter. So this reduction, however, it tells you that the area open if it is more than 50%, and the stiffness if it is more reduction in a 50%. The other thing is out of plane offset. So I have a wall below, and this is the wall above. So there is an offset of the out of plane offset, and that is the one that I told you about, the non-parallel system, that if I am in seismic design category C, this one will lead to 100% force acting on one direction, and 30% act at the same time in the perpendicular direction. Also here we have a vertical structural irregularity. That is one for the soft story and the extreme soft story. That is the irregular, soft, and extreme. And of course the weight mass, if the mass of any floor, like successive floor, have a difference of 1.5. And this one, it is for the geometric irregular. It is the same as the re-entrant corner. Okay, however, this one is 0.15. That one is 1.3. The other two, the in-plane discontinuity, it is the same as out of plane. So I have an out of plane offset. That is the one in plane. Okay, and that is the weak story. I have two types, irregular and of course extreme weak story. These types of irregularities, it is very important to consider. As you can see, I am highlighted to you to all the important points. That is one for the horizontal structural irregularity. It gives you the seismic design category application, meaning that like if I am having this one and I am having D or E or F seismic design category, then I must go to this section to fulfill this requirement. So again, I have a condition here. It tells me that I have a torsional irregularity. So to go to this section to satisfy for this type of seismic design category. So if I have seismic design category C, this part I will not consider. B, C, D, this part I will consider. Anything has a C, I will consider. This one I will not consider. Okay. If I am D, I will consider all of them. D, I think it will be considered for most of them, except for the extreme torsion irregularity. It will not allow for E and F, as we will see. So you must read this table and understand it. Also, in these cases, in the case of 1.5 and the soft story, 1A, 1B, and 2, 1A with it stands for the soft story, and this one for the extreme soft story, and the 2 it refers to the weight or mass. Cannot be, it does not apply where no story drift ratio under design is more than 130% of the story drift ratio of the next story above. So if I have like a frame, okay, 2 stories, and this one M2 and this one M1, and M2 is like more than 1.5 M1. Okay, this condition I can neglect this horizontal irregularity. However, in the case of what? So I have this delta and this delta. So if the delta 2, okay, is less than 130, where no story drift ratio under design lateral seismic force is 130% of the story drift ratio of the next story above. Okay, so you need also to satisfy that. What this most information that I am telling, it is general information. However, you need to read them. Okay, because sometimes questions will arise from any part of this. Now let's talk about the shear wall. It tells you here the shear strength of the shear walls of the shear wall frame interactive. So if I have a shear wall and a frame, then the shear must at least 75%, and the frames shall be capable of 25%. That is these systems representing the dual system, as we saw in the table. That is the one, the dual system. So if I have this is called the dual system. So if I have a special moment frame with a shear wall, it tells you that at least 75% must be resisted by the shear wall and 25% by the system. Now let's talk about the diaphragm and flexibility configuration. According to chapter 12, the flexible diaphragm condition can be considered as rigid if I have on top the steel decking or wood structural panel, or so this is a condition that I can consider as a flexible if I have a wood structural panel, and that is also an important part. Sometimes in the exam he will give you like this panel, this roof, tell you I have like a shear wall, this is rigidity equal to 3 and this one is rigidity to 5, and it tells you that I have a roof of wood panel. Wood panel means flexible. Okay, so the force that comes from here will transfer using area method, meaning that each wall will have the same force. So it is very important. Although he gave you an R rigidity and R rigidity, however he is telling you that it is a wood panel. Wood panel means flexible. So you will get distracted by these values and you will get tricked by using these values. Of course, he will tell you that to calculate the base shear on this wall, you will assume that 3 divided by 3 plus 5 multiplied by base shear. Of course, that is not the case. It will be half the value. So here it tells you that the flexible can be considered as a topped or wood structural panel, or the delta middle. That is the delta middle, and that is the delta average. Okay, if it is more than 2. This one was mentioned in chapter 12. Also to consider as a rigid diaphragm, if the diaphragm, if it is a concrete slabs or concrete filled metal deck with span to depth divided by 3, this one was divided by 2 in the case of the wind, as we saw in the previous session. Also that have no horizontal irregularities are permitted to be idealized as rigid. Redundancy. Redundancy, it is an important parameter. It usually ranges from 1 to 1.3, so it has two values, although it is 1 or 1.3. Redundancy can be used for B or C. It can be used for the drift calculation and B delta effect, the design of a non-structural component, design of non-building structures that are not similar to building. So if I have a tank, if I have a chimney, if I have an air cooler or so on, I can use rho equal to 1. A design of collector elements, splices for which seismic load effect including if sections are used. So if I am using a rho, I cannot use, if I am using an overstress and omega, I cannot use rho equal to 1.3. Design of members, this part is very important, related to the redundancy. That is the one, redundancy. It tells you that you can use the redundancy factor 2:1 for seismic design category D through F. If you satisfy these two types of criteria. So you should read it, to understand it. However, in the other cases like D through F and having extreme torsion irregularity, you can use rho equal to 1.3. Redundancy meaning that you don't have enough statical systems that can transfer the force. Like if I am having let me draw a plan. That is a plan. So I am having one shear wall in this part and another shear wall in this part. So if this one is failed, of course I will have another one, but in this side, at this side I only have this one. So it is better to have at least 1, 2, 3. And according to the redundancy here, I think this one, it tells you how to measure the redundancy of it, because if I am having a frame system, so I have a frame here, and this is one frame, and so this is another frame, and that. So I have at least 4 frames. So I can consider a redundancy. But to consider a shear wall as a frame, it has a conversion. It is related to the aspect ratio of the edge and the depth and so on. So you should read this part thoroughly. Direction of loading, as I told you, for the seismic design category B, I can apply independently, meaning that I can apply 100% from in X and 100% from Y, independent. Seismic design category C can be considered as B if it has no horizontal structural irregularity of type F. That is the one. If this one it has a type 5 of horizontal irregularity, then I will have to apply 100% and 30%. For the other systems, as you will see here, you can use where is for the other system, you will have to use 100%. That is the one. For the other system, you will have to use 100% and 30%. Now let's talk about the effective seismic weight. So it includes the dead load, of course, and it tells you the other that you need to include in areas used for storage a minimum 25%. So let me talk about this. So if I have a building and I have a dead weight equal X and I have a live load equal to Y, maybe. So if this live load it is human, so the effective weight that I am going to consider, it is equal to the dead, which is equal to the X. No live load will be considered because humans are not attached to the ground, so they are not part of the building. However, if I have a storage, so if I have a storage, it will be something like that. So there will be so they will act as a one as a building. So they consider at least 25%. So this is the idea of not considering the live load, because people are not attached to the buildings, and they can move in any direction. However, if I have a storage, I can use at least 25%. Exceptions where the inclusion of storage loads as no more than 5%. It gives you some exclusions. Also, where provision for partitions we considered in chapter 2, not chapter 2, chapter 4, the minimum of partition loads. It was, I think, 0.72 kilonewton per meter square, and can be considered as 0 if the live load is more than 3.8. However, in here, for the seismic force, even so, like, let me go to this part. The provision for partition in office buildings and in other buildings where partition located are subject to change. The minimum of 0.72 and the partition is not required where the live load is greater than that. So if my live load is like 4 kilonewton, so I will not consider the partition. However, in the effective weight, okay, you need to consider the effective. You need to consider them. You need to consider at least this value. Okay. So if in the same example, if he told me that I have a partitions, then at least I will consider 0.48 from the value, even though the live load is more than 3.83. Still, you need to consider the partition weight, because I didn't consider the partition weight. However, they are attached to the floor, so you must consider them. Also, there are the total operating. If you have a equipment, you must consider it. Any dead weight, any superimposed dead load, they shall be considered. Structural modeling, structures with horizontal irregularity. Okay, this part for the modeling, it is here. It specifies that if you have a seismic design category C, as I told you, it also affect on the impact of the, if you are going to use the equivalent lateral force or the model response spectrum and so on. Of course, the P, the equivalent lateral force B for permitted, it is allowed, especially unless all other structures. If I have a structure D, okay, you must consider these limits, or okay, it has some limits. Risk category 1 or 2 buildings are not exceeding 2 stories above the base. Structures of light frame. So he give you like criteria or limits that you need to satisfy before using especially the equivalent lateral force. Because in the complex structures like this one, maybe not maybe, you will have to use the response spectrum. Also, in this part, it tells the user the moment resisting frames that are enclosed or adjoined are more rigid and not considered to be a part of the system shall be designed. Like this one, if you didn't provide enough expansion here, okay, so there is no direct connection, this part will be very stiff, so the moment will be like, let me draw it. So I have like a floor, and here I put the walls, okay, so the moment will be something like that, okay, it will very high at this part. However, if I provided like expansion here, so the system will be here like this, so the maximum moment will occur at this location, okay. Also, the behavior of the structures will be not the same as you expected. So it is better, of course, for any non-structural component like the walls or partitions separated for the main statical system, to ensure that the statical system behave the same way as has been designed. Okay, so the structure with horizontal irregularity, diaphragms have not been classified as rigid or flexibles. That is the one. You must read it, okay. Also, that is the one I told. We will start with the equivalent lateral force. As I told you, you can design using the elastic response, which is VE, or you can divide it by the R. That is the case. We are using the benefit of the material, of the ductility of the material, so not to increase the sizes and so on. It is economical. So that is the idea of the equivalent lateral force. It is equal to the force multiplied by acceleration multiplied by the effective weight. The CS, of course, it is the SDS multiplied by the I. The I is the importance factor from chapter 1, as I told you. He will not tell you what is the importance factor. He will tell you that you have a residential, you have an important essential building, and so on. So you can consider I equal to 1 or 1.5 or 1.5. And after calculating the TS, he tells you that it shall not be less than, if the T is less than the TL, that is our case usually, then it will be equal to, it shall not be less than this value, not more than this value, and the minimum of it, this one, and at least 1% of the dead weight, this criteria or these limits from chapter 1. So if you have a building, and he tells you what is the minimum base shear, okay, can be imparted on the structure, so you can consider, of course, the limits. I have is an SDS and IE. So if he just gave you the SDS, he gave you the SDS, and he told you that it is a commercial, so the I it is risk category 2, the I equal to 1. So I will multiply just by these forces, okay. I will consider this one, and it shall not be less than this one. So it is an easy question. It is very straightforward. But when he will give it to you in, as I told you, the exam is an 80 questions. So when he will give you this example with many codes that you have and a lot of data information you already have, it will be a difficult one. You will not be able to think, okay, that is a question. Yes. So he will tell you what is the minimum base shear affecting on a building, and they just give you the SDS. Of course, consider the equivalent lateral force, the minimum force, that is the one. Okay, so as I told you, get yourself familiar with the code, so it will be easy for you to transfer between the pages and understanding what type of questions and which data you need to get from the code. Another important point is period determination. The TA for approximate, it is depending on the system, the statical system, and the height of the structure. And we told that the structure is the height of the structure. It is starting from the base to the top point of the structure. And he gave you a limitations. So what is the difference between this T and the TA? My system, okay, if I'm using a software, I'm using ETAPS or STAD. He can determine the T based on the deflection of the structure. Okay, so he can determine the T of the structures, and of course this T, okay, shall not be more than. So if I have like a response spectrum, okay, so the T that is been generated from the software, it will be like here. However, the T approximate multiplied by CCU, it give me an upper bound, so it will give me like this limit you cannot pass. If your T, this one, was here, then you will use this one, which is corresponding to the limit. Okay, so the TA, I'm using it as like an initial, I can use it as a preliminary design and so on, and I am also using it as an upper bound for the T that has been calculated through the software. Also an important part here, for structures not exceeding a 12-story concrete or steel moment resisting frame, average story height is at least 3 meters or 10 feet, meaning, okay, so the T approximate can be considered, it is the number of stories divided by 10. This type of like empirical formula, it is very important, because at sometimes he will not give you he may give you like to differentiate between the TA generated from this equation, calculated from this one, and the TA which is equal to also to this one. Okay, so if he didn't give me enough information about the time period and I want to calculate the time period, of course you can use this one and you can also use this one. So get yourself familiar with them, because sometimes you need to get the time period of the structures. We will show that in the examples. The vertical distribution, okay, the vertical distribution, it is not like it is not a uniform shape. The vertical distribution will not be this one and that one. It will not be uniform, depending on the time period. As the time period of the structures increases, so it will not uniform distributed at each floor. It will have a factor called K. So if the T is lesser than 0.5, that is the case. Maybe, okay, I will tell you something like I have a building, okay, and he tells you that the average height between stories is like 5 feet, not 5 feet. This is the one it at least called 3 feet, 10 feet maybe. So I have at least not 10 feet, at least 12 feet. Okay, and he will tell you that I have a 10 story. The average of them, and he will give you the total height not given, that is called an H. So he need you to he wants from you to calculate the base shear, the distribution, and he tells you that the base shear from the seismic is equal to like 200 kilonewton, and he tells you that to calculate the base shear at story number 4. So I have a 10 story, the average height is 12 feet. That is the average, so it doesn't so the total height, I don't know the total height, so I can use the T approximate if equal 0.1 multiplied by the N, okay, which is equal to 1 second, okay, and after considering this 1 second I can get the K factor, okay, and after getting the K factor I have the dead weight for each floor. So he gave me the dead weight of each floor, so I can calculate the vertical force from this equation. So it is very important to consider these empirical equations, because sometimes he will not give you the total height, so you will not be able to solve this one. He will just give you the number of stories and give you just the average. Okay, so the total height it will have a differentiate, because some height will be 10 feet, the others will have like 15 feet, so the average it will be 12. Okay, so in this case I will use this one, getting the value of the K. If I have a T equal to 1, I will get the value like T is equal to 1, I will get the K, and then I will know the distribution at which floor he asked me to solve. So it is also an important question for the vertical distribution. It is very important to consider considering the time period here to which will affect the K. It is an important question in the exam. So the vertical seismic, it is like a brief. If T is given, it checks the upper limit, TA multiplied by Cu. Of course, it is also important. If not, calculate it. How to I will be able to calculate it, whether this method or this one, depending on the information. Determine K factor for distribution. Calculate story shear force. The horizontal distribution of forces, it is based on the relative lateral stiffness, as I told you, the rigidity of each element, and it will be transferred. Of course, it depending on the diaphragm. As I told you, if the diaphragm is rigid, then it depending on the stiffness. If it is flexible, then by the area method. Now we will talk about torsion. There are two types of torsion, and the torsion it is explicitly for the buildings with rigid diaphragm. As I told you, applicable for rigid diaphragm. So if I have a flexible, there will be no torsion. Okay, the system will not be able to transmit the forces to the lateral resisting system. Inherent torsion, it is generated. Okay, let me draw it. So if I have my system here, I have like a core, and I have a shear wall here, shear wall there, and another one, and so on. So the center of mass will be something like here, that's the center of mass, and the center of rigidity will be something like here. So we know that the seismic, it is based on the mass, it is inertia force. It is inertia force acting on the mass, so it will act here, the center of the mass. However, the one that going to resist it, the center of rigidity. So the distance here in like in the x direction and the y direction, okay, it will be the eccentricity. That is called the inherent. Okay, that is called the inherent. However, the accidental, what does mean by the accidental? If I have that is the dimension of the building L, and that is one is B. The accidental, it specifies at least 5% of the direction perpendicular to the seismic. So in this case, I will consider 5% of the L, and in that case, I will consider 5% of B. Okay. Of course, it is better to move away from the center of rigidity to increase the torsional effect. Okay. Also, the accidental torsion, it is important point. It is caused by assumed. It has an amplification factor. So if I have any of these seismic design category, and I have torsional irregular torsional irregularity, or extreme torsional irregularity, I will multiply by factor AX, and this AX, it actually ranges from 1 to 3. So it has a range from 1 to 3, and of course 1A, it specified that the delta maximum is more than 1.2 delta average. Okay, so in the case they are equal, in the case in the delta maximum is equal to 1.2 delta average, then this one will be 1. Okay, that is the resulting from the eccentricity between location of center mass and center of rigidity, 5%, and so on. Now let's talk about story drift determination. Before talking to that, I will have to draw the same one for the force and the delta. That is the delta and that is the force. Now I am going to draw that is called the elastic. Okay, but we are divided by R, so we are designing here. That is a design. However, we have the delta. It will be the delta elastic. Okay. To get the delta inelastic, we will have to multiply, that is the delta inelastic, we will have to multiply the delta elastic by CD. Okay, because at this point you will need to understand the delta 1E, okay, and the delta 1. So the delta 1, it is generated from the delta 1E multiplied by the CD. Okay, that is the idea. So the delta X is equal to the CD multiplied by delta XE divided by delta E. Delta X, I can say it is the delta 1. Okay, so the delta 1 in this case, it will be multiplied by the CD multiplied by delta 1E divided by the IE. Okay. However, that is if we are considering the first story. However, for the second story, it will be the difference between the delta 2 and divided by the delta 1. So if I have, let me draw it. So my system, if I have like a bin here, so it will behave something like that. The actual case that I am designing, that is the delta 1E, which is based on the FE divided by R. But to consider the inelastic response, we need to multiply by delta 1E multiplied by CD. So it will be this one, delta 1. That is the delta 2. Of course, we need to get the difference. Okay, to get the difference for each one. So that is the delta 2E also, and after multiplying by the CD divided by E, I will have the delta 2. So that is the actual the inelastic response by the structure, and that is the one that we are going to check. To check the story drift limitations, it will be the difference in the difference between the drift in each story, and according to the risk category, and the statical system, I will consider which limitations or which limitations that I'm considering, like 1% of the H, or 1.5, or 2% of HSX. HSX, it is the difference between the story height. Also, don't forget that if I'm designing for any seismic design category D or E or F, as we already saw in the one regarding this row will consider is in drift calculation and B delta effect. So we in calculating if in my case I have a seismic design category D or E or F, I will still use in the drift calculation or B delta effect, I will still use the rho equal to 1. However, this rho is not included in the allowable story drift. So to include them, I will have to divide it by rho. Or in another case, I will multiply the actual forces as the strength level by rho, and the actual delta coming from this case, considering it the delta allowable. So don't get confused. If I'm designing for seismic design category D or E or F, for checking for the drift, I will use rho equal to 1. However, the allowable story drift, I need to divide it by rho. The B delta effect. Okay, this equation it is related to the division of the secondary effect divided by the primary moment. The secondary moment divided by the primary moment. Meaning that if I have a B, and that is the height called the H, and I have a V, so in the deformed shape of this structure, it will be something like that. So I have a delta. That is 1B. So I will have a secondary moment, M secondary, which is equal to B multiplied by delta, okay? And of course I have a main moment, V multiplied by H. So to make sure that the structure is still stable, so the secondary moment must be lesser than the main moment, okay? So he will get a value called theta, which will be equal to B multiplied by delta divided by V multiplied by H. However, the delta that he is going to use, the delta elastic, not the inelastic. So he will have to divide by CD multiplied by I. And that is the case here. He will have to divide by the CD multiplied by I. Okay. The B and V and the H is the difference, the height difference between the floor height, or the difference between two-story height. The BX, let's go to this one. The BX, it is the total vertical design load at above level, no individual load factor, meaning that it will not consider the factors of 1.2 dead load and so on. The total vertical design load, the total vertical, it will be generated from any load case corresponding with the seismic, like the live load will be considered, because there is a case of the seismic and live load and the dead load. And the Vx, it is a seismic shear force acting between these levels. So if I have two level, that is the one is concerned. So that is the HSX, and that is the V, that is the B, and that is the V. It will be the same like that. Okay, that is the idea. It will be the total dead load. The V here is the HSX, and you will have to consider that is the equation. It is an easy one. It tells you that if the theta is the theta maximum must be more, that is the theta maximum. If the structure is more than that, then the structure is unstable and you have to choose another system. So if he give you, like in the question, in the exam, a question related to you that the statical system is satisfactory or not, you will have to measure the theta. Okay, so it will be an easy one, because of course you need to consider the CD. You will get it from the tables. I depending on the type of the structures and the risk category. The delta, he will give it to you. The HSX, of course it will be shown, and the VX and the BX, of course it will be direct question. But you must understand that if the theta is more than 0.125, then the statistical system is not satisfactory and you must change it to be more stiffer. That is the maximum value, of course, of the theta. Here it talks about that this part, it considers if you need to consider the B delta effect or not. If the theta is lesser than 0.1, you don't need to consider the B delta effect. If it is more than 0.1, you should consider it, or you shall consider it. It is a mandatory, and you need to check the theta against the theta maximum from here. That is the idea, because as the secondary moment increases, the B delta effect will increase, and of course, as you can see, it will behave. The secondary effect will have more effect on the structure. So in this case, if the secondary moment has a higher value, then you should consider the B delta. If it is small, like the zeta is less than 0.1, then it will negligible. So it will be something like here. So it will be negligible. Now let's talk about the model response spectrum analysis. Of course, we know that the model, it is important for the complex structures, and it has a limitation like at least 90% of the actual mass to be considered. And of course, the scaling, at least 100% of the base shear using the equivalent lateral force must be included, and so on. And if not, if the actual forces, or if the seismic base shear from the response spectrum is like 90% from the equivalent lateral force, you still have to multiply by this scale to include the all to make it similar to as equivalent lateral force. Let's now talk about the diaphragm, chords, and the collectors. In this part, if I have a system like here, or a frame, and my statical system, it is a steel frame, and this is a plan, a concrete plan. This that is a frame, okay, which is in this direction, depending on the statical system of this concentric braced system. So these beams will be called struts, or can be called collectors, or ties, and so on. This is in steel. However, in the concrete, so the idea of strut or collector or tie to transfer lateral force to the vertical system. So if I have like shear wall here, shear wall here, shear wall here, and so on, and I have a force acting here, this part will act as a collector. This part will act as a collector, okay, because in the case if it is reversible. So the areas that need to transfer, of course, this part is called a diaphragm. But in this area we can call it as a collector, like this area. If I have a direction of loading from here, so the forces need to transfer to the shear wall. So this part can be considered as a collector, as a collector, as a collector. As I told you, I can consider it as like a bin, and that is a beam. Let me write logic. So if I have I can consider it as a hinged, and this is a beam. So the moment will be something like that. So this can call the main diaphragm chord. That is like maybe we can call it the lower chord. This one can be called the upper chord. This one has a compression, tension, and this one has a compression. Okay. Another important part is the simplified method seismic base shear, and I am telling you to focus on this area. Okay. This area, maybe we'll talk about the linear response history analysis. That is very deep topics and very advanced topics. I don't recommend even read it unless you are dealing it with your work. But don't waste time on these parts. Diaphragm chords, collectors. In the example part, we will talk about it. Just read the diaphragm design forces. Just read these parts. The one is highlighted in red. You should read it. As I told you, that is part called the collector. So there is a shear wall. There is a column and shear wall this area can consider be as a collector. That's a full length shear wall, no collector required. So when you design this part, the area between here, it will be considered a collector, and the requirement for the collector will be need to fulfill this area. Okay, the simplified, that is also the structural walls and other anchorage. The design of the out plane forces, you should consider this part also. The drift and the deformation, that is where we talked about it. The reduction also. The simplified approach will be something, no, not this one. It will be, yes, that is the one. The seismic base shear based on a simplified approach. This simplified approach, I just focus on this part because it is an easier part, meaning that if he just give you the SDS and give you the type of the building, so you can get the R, the F, it will be like for a building that has 1 story above grade, then it will be 2 equal to 1, 2 story, 3 story. So if in the exam give you like a 3-story building, okay, with just the SDS, and he tells you what is the base shear, what are you going to do? No information. Just this building like a special moment frame, and the total weight of the structures, that effective weight is X. So he just give you the main idea, so you will get the R factor from the table, and so can you calculate it if you don't know this equation? Of course not. So 3-story, I will use 1.2. The SDS, it is given, W is given, R I will go and check it. Maybe he will not give you the SDS, he will give you the SS, okay, and he will tell you that it is a rock site. So in this equation, in this example, you have a rock site, okay, you have W effective, system special moment frame, you have the SS, it calculates the base shear, okay.